This is example 12.5 from Discovering Design with Chemistry, and we're going to look at some redox reactions and get them balanced in this example. Balance the following redox reaction. We have copper plus some iron ions being reacted into becoming copper and iron ions, but with different numbers. So let's first look at the numbers that we're working with here. This one has a 0 charge. This one has a 3+ charge. We can also write 3 little pluses if it helps you to see it that way. This one has a 2+ charge, and this one has a 2+ charge. So overall, if we look at the two sides, this has a 4+ charge, and this has a 3+ charge. What's happening is that our copper is going from 0 to +2, so it's gaining 2, or it's losing 2 electrons, but it's gaining 2 in charge. And the iron is going from a 3+ to a 2+, so it's losing 1, it's going down 1 charge, it's gaining an electron. And so if we could have the iron gain 2 electrons, that would fix it. So in this case, what we need to do is just simply double the amount of iron that we're working with. And so if we put a 2 here, that means we now have 6 charges happening here. So the overall reaction on the side is a 6. And then we do the same thing here so that the numbers of atoms and ions and molecules stays balanced. Then we have another 2 here. And this number becomes, well, I guess I could write it 2+, but times 2. And so that means 4+ for this section. And 2+ and 4+ becomes 6+. So now it's balanced in both sides. And so you can see that we have just as many plus signs on this side as we do plus signs on this side. And we can see that not only are we balanced in that we have 1 copper atom on this side and 1 copper on the other side, 2 irons on this side, 2 irons on that side, but we also have the charges being balanced on each side. Okay, so let's look at the other one. Ooh, I might need to restart my computer before the next example. It is slow. All right, in a redox reaction, iodine 2 is reduced to 2I negative, while Fe is oxidized to Fe3+. What is the balanced chemical equation? All right, so we know that it says I2 aqueous is being reduced. In other words, that's what's happening to it. So that's going to go on the other side of our arrow, while Fe in its solid state is being oxidized to Fe3+. All right, so we have the bare bones, kind of like we did in the last one. So we have the things on the right side. Because this is being reduced, I knew that which side to put the different pieces on. All right, so this has no charge right now. This is 0. This is 0. And they told us, so we don't even have to think about it, but the iodine's being reduced because it now has a 1- charge, but there are 2 of them. So if I were going to draw that, I could draw a minus and then another minus. And this one has a 3+ charge, so I could draw 1, 2, 3. I drew them sideways to show that it's all 3, like these are all in a line sideways to show that it's just one ion that has a 3+ charge. And then these, I did one under the other to show that one of them had a 1- charge and another one had a 1- charge. It doesn't matter, as long as I draw enough pluses and minuses, it helps. So overall this side is a 0, and overall this side is 2 times -1, so that's -2 overall, and +3, so this side has a 1+ charge. And so my charges aren't balanced. I need to fix that. So let's see what's happening here. We have the iodine. We know that it's being reduced, and it's going from 0 to 1-, but because there are 2 of them overall, it's going down 2. Is what's happening to the iodine. And then the iron is also starting at 0, but it's going to a 3+, and there's only 1 of them, so I'm just going to repeat the number. So the iron is going up 3. In this case, you might look at what's overall happening to each of them and be like, 2 and 3, I can't just double 1 like we did in the last problem. And you're right. So the easiest way to figure this one out is to look at 2 and 3 and think, what do they have in common that they can both become? I can't double one to make the other, but I can use what I know, like when we're doing fractions in algebra or other things and I need them both to be the same. I can find the least common multiple that they work together. And so for 2 and 3, that would be 6. So if this can become a -6 and this one can become a +6, that would fix the thing. They would both be gaining or losing the same number of electrons overall. Let me switch pen colors real quickly. Okay, so if I want my iodine to lose 6 things, I need to have, there needs to be this. I'm not going to worry about the left right now. I'm going to worry about this one because this is where the charges are happening, so it's easier to see. So I'm losing 2, but I want to lose 6. So let me change this to 6 and keep it lined up. So if I have 6 of them, that means, and each one has 1, instead of having a 2 like this, in fact, I probably should write them going down so it makes more sense. This is only a -1, so let me write them going this way. I need it to be 6. I now have, instead of 2 things here, I have 6 things here. So this 2, let's erase that. Oh, my computer is super slow. Is going to become a 6. So I have 6 iodines on the product side. Over here, I have I2, so I can't just stick a 6 in front of that because the iodines are, it's like having 2 little atoms together in a molecule. So if I want 6 of them, I have to have 3 pairs of those. And so this one's going to have a 3 in front of it. And then the iron, again, because I'm working with the charges that they are becoming and I have zeros on the left, I'm going to focus on the right, on the product side. I need this to be 6, and I'm going to keep them in the same. They're in a row of 3, so I'm going to keep another row of 3. Okay, so I had 1 row of 3. Now I have 2 rows of 3. To get 6 charges, I need to have a 2 here. And you could also, instead of drawing little plus signs, you could also look. I have a 1 here. I need it to be 6, so 6 goes in front. I have a 3 plus here. I need it to be 6. 3 times what makes 6? 2. So a 2 goes in front. And just like with the other one, if I have 2 irons on the right, I need to have the same number of irons on the left. Now, in this case, Fe is just plain by itself. There's no subscript like the iodine had with the little 2. So this one's just going to be the exact same number. So I bumped the other one up to 2. I bumped this one up to 2. I'm going to erase some of the little extra numbers that we had here. We can look at them overall, but not write them down so that you can see what's happening. So I have a charge of 0 on the left because nothing had a charge, so multiplying it by more things didn't change that. And on the right, I have a -1 on the iodine, and I have 6 of those. So -1 times 6 is -6. And then on the iron, I have 3 plus, but I have 2 of those, so I have 3 plus 2 times, and so that's +6 or 6 plus. And so the iodine gives me a 6 minus, the iron gives me a 6 plus. Those two together make 0, which is the charge that the left had. So the 2 balance in charges. And there are 3 times 2 iodines on the left, which is 6. And there are 6 iodines on the right. There are 2 irons on the left, and there are 2 irons on the right. So both the number of atoms on each side balance and the charges on each side balance.